Here we go. All right. Good. Now we're recording. Now that we're all in 100% agreement on that. All right. I'm not recording. Official. All right. All right. Very quickly, the things that we had talked about yesterday. Of course, obviously, the number one thing was this idea of the derivative. Okay, but we had these two equations. You should be able to work with those. The next quiz, I may or may not give you those. So be prepared to know those from memory, okay? Those two equations. Okay, the height of an object in free fall, where gravity is the only thing acting on it, okay? And the velocity of an object in free fall, those two equations, okay? V sub 0 is initial velocity, H sub 0 is initial height from which it is thrown or dropped. Then we have the speed limit law, which we wrote down, okay, which basically says if we know something about the slope of a graph, then we know something about how much it goes up or down, right? Because rise over run. So if we know something about the slope of a graph, even though it's changing all the time, we know something about how much it goes up or down. Or if you want to talk about velocities, if we know how fast you're going, or if we know something about the rate, then we know something about how much the amount changes, right? In this case, the miles, how far you went, or whatever, okay? And then this, of course, is the main idea from yesterday, which is this idea of f prime of x, the derivative function, and it is its own function, and it represents, you can think of it one of two ways, the instantaneous rate of change of the function f, or the slopes of f, okay? That is the derivative. Now, notice I put some units there. We were talking miles per hour, but it could be dollars per pound or feet per second. Or as you saw in problem number 41, something about daylight hours. Daylight hours, right? Because right now, what's happening to the daylight hours? They're decreasing, right? The days are getting shorter. Matter of fact, I think this weekend is daylight savings time. Changes, I think, right? So the days are getting shorter as far as daylight hours. Okay, they're changing each day, a little less, right? So that's daylight hours per day would be our units, for example, on number 41, which we'll talk about here in a little bit. So rate of change can be, different types of units. And it's always the y units divided by the x units of the original function. So if you have function f that has miles, x units are hours, then the derivative is miles per hour. Now, if you want to do the rate of change of that, if you want to do the derivative of f prime, which we said is f double prime, then that'd be miles per hour divided by hours. Miles per hour, that's acceleration. So the first 12 questions in the homework had you interpreting those things. Now, we had done some of those already. Very important that you can do that. Talk about things that will be on our next quiz. I'll guarantee you our next quiz will have something like those first 5 or 6 questions in. Okay, or question number 41. What are you looking for? Cats? Somebody got it? Is there any extra ones? Okay, so number 1, P of 2 equals 100. We talked about that. At noon, if you look at the description, at noon, the car was 100 miles east of Bismarck, because east is positive. What does it mean? P of 0 is negative. Less than 0 means negative, right? What's that mean? Number 2. P of 7 is negative.
10 miles east.
It just says, number 2, what does the statement P of 7 less than 0 mean? At 7 o'clock, not that it's traveling west,
But it
is west of Bismarck. And those are two different things, right? P is the position of the car. So if it's negative, that means west. It's west of Bismarck. It could be stopped. It could be coming back to the east. It could be going west. We don't know. But we know that it is west of Bismarck. So again, be careful with what you say so we don't get in an argument after we go over the next one. All right, number 3. What is the statement? And we might anyway, that's fine. V of 2 equals 70. So we said that yesterday. At 2 o'clock, the car is going 70 miles per hour eastward. But we don't know where it is, right? I mean, just by that statement alone, we just know it's going eastward at 70 miles per hour because it's positive. And then the next one is negative, so that means it's going westward, okay, at 60 miles per hour. V equals P prime. What does this say about the relationship between P and V? Don't make it harder than it is. It just means that V is the derivative of P. So P prime equals V is just saying that V is the derivative of P. You could say rate of change, or you could say slopes in there, but really just the word derivative is fine. Okay? And then the same thing with A equals V prime. That means A is the derivative of V. A was acceleration in that scenario, right? Was acceleration. All right. And so suppose that P is measured in kilometers rather than miles. Well, then P prime would be kilometers per hour, right? The Y units divided by the units. Okay, so I wanted to get into that. Now, 11. Well, no, I take it back. I do want to talk about number 10, and this actually, you know what? We'll take care of number 10 when we talk about number, I think it's number 47. 47. Okay? We'll talk about 47. Now, and because 47 and 10 are very much the same thing, equation, tangent line. Number 11. Suppose that B is the balance in a bank account in dollars T years after the account's established. What does B prime mean?
The rate of increase.
The rate of increase or decrease.
Or decrease.
You hope it's an increase. Keep going.
Of the balance.
Per year. I would throw in the per year. Anytime you're dealing with a derivative, man, you're dealing with something per something, right? It's a rate.
Could you just put balance per year?
Balance per year. Dollars would be good to throw in there somehow. But it's the rate of change. The rate of change of the balance per year. So the units would be dollars per year. Okay? That's what B prime is, which of course you would be interested in, right? If it's positive, it would be an increase. If B prime is negative, it's going down, right? Now most bank accounts wouldn't go down necessarily, but like a stock or something, right? Something that an investment that way could be that kind of thing. All right. Next thing I wanted to talk about was 14 and 15. Now I apologize, didn't really, which is fine. I mean, I didn't do an example of this, and we don't always go over every possible example. That's the whole point. I really like, what I like about this book is the problems are not, it's not like, if you think back to algebra class or even trig class last year, the teacher stand up there and work 2 or 3 examples or 4 or 5 or whatever examples, and then you would do 21 through 71 odd, or maybe you always had to do the evens, I don't know, whatever. And they would be by sections, and you do like 10 of the same kind of problem because you were practicing these skills that you would need, and that's what algebra was about. And advanced math somewhat like that. And there will be times here where we have certain skills we need where we'll practice problems over and over and over. But really it's about, if you looked at that, you'd think, my God, every problem's a story problem. A lot of words, right? A lot of reading words and what does it mean? And that's true. And so a big part of the homework and the stuff is discussing. I love what you guys do. When I give you guys work time, it gets loud in here because you're talking and you're arguing and whatever. That's great. That is really important as far as understanding what's going on, right? So I didn't, say, hey, do this, but when you get to, I think it was 14, is that right? Was F prime and -2 for this picture? So what they're saying, so when we first talked about derivative and slope, we said, I'm recording, right? We said that it's the slope of the tangent line. Really by definition, that's what derivative is. We said it's rate of change, it's slope, but what do we mean by slope? What we mean is the derivative at a point is the slope of the tangent line to the curve at that point. So when I ask for F prime of 2, matter of fact, this is a big part of what our next section is about, is what are some ways we can find the slope at a point? How can we find the derivative, right? And so we're going to investigate that today a bunch of different ways. Well, one way is this. If all I have is the graph of f, and this is the f graph, if all I have is the graph of f, well, one way to find f prime and negative 2 is sketch in the tangent line. Your next quiz will have some of this too. I'll give you a graph like this, and I'll say estimate f prime of 2. Okay? What I'll expect you to do is sketch in your tangent line like so, and just do a rise over run. Now, it makes it easier if you do a run of 1. So I usually try to do a run of 1, and I extend my line far enough so I can see what the rise is. Well, that looks like 5, 6, 7, 8, 9-ish. So I would say approximately 9. If you had 8, if you had 7, what I will do to grade that is I will look at your tangent line, right? Because you're guessing a little bit there. So if your tangent line looks like it came in at about 7, I'm okay with that. Now, I don't see any way it could be below 5. I mean, the only way you could go over 1 and up 5 is if that line went like that, and that would be a really bad tangent line, okay? So somewhere in the 8 to 11 range probably is probably pretty good. And then 0, again, now through here, the curve is pretty straight, so the tangent line pretty much follows the curve. But anyway, over 1 and down, I don't know, about 5 or 6 probably, but it'd be negative. Don't forget the negative on it, right? So that's it. That's it. All right, let's go to 25. 25 was the speed limit law, right? The speed limit law. Now, talked with several people this morning, and some of you were wanting to use the formula, right? And I'm okay with that. I just think it's important that you really understand what's happening, though. But if you just plug numbers in to the formula there, then you can get this, and that would be acceptable. So what I think some of you were doing is you did, okay, they're asking about h of 5. So you did h of 5 minus h of 0 is less than or equal to m, which is this right here, negative 2, and then 5 minus 0. And so they told me h of 0 is 0. So this is h of 5 minus 0 equals negative 10. Oops, less than or equal. So h of 5 is less than or equal to negative 10. Okay? And that's attractive from the standpoint of it's just plug and chug, right? I mean, it's just, here's a formula, just plug it in and go, right? The downside is not really understanding what you're doing. You're just putting in numbers, right? So that would be acceptable to me, but there are a lot of different ways to ask a speed limit law problem. And so understanding the concept behind it, I think, is really critical. So what I would suggest here is, let's talk about that. So what I said yesterday, I said, okay, here's my h function. They tell me h of 0 is 0, so that's there. They tell me this, which means what? Less than or equal to, which means it could be like negative 3 or negative 4 or those kind of numbers, right? So that means if I go over to 5, right, and I'm starting here at 0. So if I go over to 5, so that's a run of 5, and my slope is negative 2, that means I'd have to go down 10 or more. Because if the slope was negative 3, then I'd go over 5, I'd go down 15, right? So it looks like h of 5 has to be negative 10 or lower, which of course is what that says. So a picture with a few words saying, if you go over 5, you have to go down at least 10, but you might go more than that, so h of 5's got to be less than or equal to negative 10 is a really good explanation, really shows you understand what's happening, okay? Again, just putting into the formula is acceptable for an answer there too. Okay, is h of 3 less than or equal to 5? So again, if we do just the plug-in thing, it would look like this. h of 3 minus h of 0 is less than or equal to negative 2 times 3 minus 0. H of 0 is just 0, so this becomes just h of 3 less than or equal to negative 6. Now some people, if they, again, here's the problem, if you really don't understand what you're saying, you'll get this, you'll say, oh no, that's not true. I didn't get that. Well, no, yeah, you did. You said what we know is that h of 3 is less than or equal to negative 6. For sure, it's negative 6 or lower. So is it true that h of 3 is less than or equal to 5?
It has to be.
Yeah. Yeah. Right? Is h of 3 less than or equal to 5? Absolutely, because what is it? It's negative 6, negative 7, negative 9, 8, 9. Those numbers are all less than or equal to 5. Those numbers are all less than or equal to 5. Right? Now, you might be saying, but yeah, what about 4? What about 3? What about 2? H of 3 can't be those, right? That's what we just showed. H of 3 isn't those numbers, right? H of 3 is less than or equal to negative 6, and those numbers are all less than or equal to 5. Okay, now, just talking it out, it would look like this. If I go over 3, right? If I go over 3, then that means I have to go down 6, right? So that'd be here at negative 6, which is right here. Or it could be lower, right? So here's all the possible values of h of 3. Is it true that h of 3 is below this point right here? Is it a true statement that h of 3 is less than or equal to 5? Yes.
The way I went about it is, so if it is at 3 and 5, it has to have a positive slope from the origin, right?
Right.
And if the slope is less than or equal to negative 2, then by definition, the slope can't be positive.
Right.
Therefore, h of 3 is less than or equal to negative 5 is true because
h of 3 is less than or equal to 5 is true,
5,
right?
excuse me.
Because, right. Yeah, that's
that
what
way you
would
can
work.
go
Yeah.
back to.
Yep, Macy.
I'm confused by that, like why h of 3 less than or equal to 5?
Oh, yeah, because,
It can't be 5.
right.
It implies that it could be 5, but it can't. So
Right.
I don't see how it's really true.
Computer programming, we talked a lot about the word or. Or means it can be one or the other, right? Or both. Well, it can't be less than and equal to. But as long as it's one or the other, then it's still okay, right? So less than or equal to 5. So again, I have $10 in my billfold, right? I have $10 in my billfold. Is it a true statement that I have less than or equal to $1,000? Is that a true statement? I have less than or equal to $1,000. Yeah. Right? And again, the equal to, you would say, well, why don't you just say less than 1,000, right? I mean, that's what I have is less than, but I can throw the equals in, it doesn't matter. But, I get it. I see what you're saying. You feel like it could also be that. Because when you're in algebra class and you're doing graphs and you're saying less than or equal to 5, you say, well, less than 5 and it could be 5, and, Yeah. Anything else about that? Okay. All right. So, those are both okay on 25. All right, 28 is another one, except they word it a little different. What do they say? They say, what are the possible values of f of 1? Or what does it say on 28? What can be said about the values of f of 1 and f of negative 3, right? So it's kind of the same thing. So again, I would draw myself a picture. Here's the f graph. F of 0 is 2, right? F prime is greater than 4, so it could be 5, 6, whatever. So f of 1 means I go over 1. So if I go over 1, that means I have to go up 4 or more, which would put me at what? 6, right? Because I was at 2. So if I go over 1, I go up 4, I'm at 6, but it could be up higher than that. So what can be said about f of 1? Greater than or equal to 6. But could I say, now, so f of 1 is greater than or equal to 6. Okay? All right. And then negative 3 is negative. All right. Let's move on to this section. Okay? 32 through here. Okay? Suppose that an object can move only along the positive x-axis. Sketch the object's position, velocity, and acceleration graph. Okay, so what are these the ones we did? 32, 35, 37? Okay, 32 says if the object is moving away from the origin at a constant velocity. So that's Bismarck, is like the origin. Away from the origin at a constant velocity. Where'd you go with your graph? Straight diagonally?
Yeah.
Could you have went down?
Yes.
Would be the difference. West versus east, right? Or left versus right, or whatever, right? So it could have went down. Let's do that up, and let's do one down in blue. Either one of those. You could have done the red or the blue, right? And why does it have to be a line? Why does it have to be straight? The word constant was the key there. Constant. If they just would have said you're moving away from the origin, could have been curved, right? Could have been a variety of things, but had to be straight. All right, now the red one. What would be the velocity if that is your position graph?
Horizontal line.
Horizontal. I'm glad people didn't say straight. Horizontal line, where?
Positive area.
Above the x-axis. If you would have done the blue graph, right? Right? Because, now, what do we want to think about? Remember, velocity is P prime. P prime means slopes. The red graph has a positive constant slope. So, 2 slope the whole time. So over here, the y value should be 2, right? Here, the slope is -2, -2, or whatever. So the y value over here should be -2, -2, -2. Okay. Acceleration is the derivative of velocity, and what is it? The second derivative of position, right, is the acceleration. But all I really care about is it's the derivative of this graph. So this graph needs to be the slope of this graph. So let's do the red one. Horizontal line at 0, because the slope of this graph is always 0, so therefore the y value of this graph has to always be 0. What about the blue graph?
Same thing.
There it would be the same thing. Exactly right along the x-axis. All right. 35. 35 says, the object first moves right, then moves left. So moving right would mean it's got to go up. Straight or curved? Doesn't say. Doesn't say. Okay? So let's do one where it's straight. So it moves right. Then what happens if it goes left?
Straight down.
It comes back down. Okay? Or we could have done one where it curved. We could have said something like that. Right? Either one of those would have been okay. Which one is, what's that?
Is it okay if mine extended?
That's fine if you went that back. They didn't say it came back to the origin, did it? Right. So it could have came up and came back a little ways. It could have came back down, whatever. Okay? Now, which one of those is more realistic physically? The curve, probably. You probably maybe speed up, you slow down before you come back to the left. This would be like an instantaneous, right? This would be like going 50 mile an hour and then instantly going 50 mile an hour the other way. Probably not going to happen, right? Okay, so let's talk about the velocity of the red one. So what would the graph be over here now, this one? Does it have to be horizontal there? It's the same thing we did here. Constant slope the whole time, so therefore its y value has to stay constant, and then what? Right? And so you better have like an open circle or something there, right? That again shows how that's physically probably not possible. right? To make that instant change. Now maybe you drew a straight line, then kind of curved it at the top, and then drew a straight line. Whatever. That'd have been okay. Then maybe it would have just kind of come down here steeply, that kind of thing. Okay. What would the blue look like then?
Downwards.
Yes.
Good job. It would be this right here. It would be something like that. Now let's see why. Let's think about it here. Now, could it be curved? Could it kind of come down like an S kind of thing? Maybe. Yeah, it could. It could. Okay, but let's talk about why it's got to go down. Some of you were doing this. It's not going to go up, right? Because think about what's happening. The way I've got it curved. Now, I suppose it depends the way you curve this. Okay, where you curve this original one. Because we had a lot of options here. What's the slope here in the beginning? Positive and pretty steep. So like a big positive number. So this y value has to start as a big positive number. Now what are the slopes doing here? They're getting less, right? They're positive slopes, but going like 4 or 3 or 2 or 1, right? So these y values got to be going 4, then 3, then 2, then 1. And then what's the slope up here? 0. And then the slope goes negative and getting bigger negative, right? Just like that. Okay? All right. The key, though, the key to graphing these was what we talked about yesterday. The slope of f graph is the y values of this graph. So now we're going over to here. So the slope of this graph is the y values we're going to put over here. So let's do the red one. What are the slopes? 0, 0. So it's just going to be on the x-axis. What about the blue graph? No.
It goes like up a little and then just sinks down.
Not if I have a line.
Is it positive?
If I have a line, if this is truly a line, now we said it could have S-curved or something, but if this is truly a line, what are its slopes?
It's just 1.
Negative, let's say it's -1. What's the slope here? The slopes here are -1, let's say, or -2 or whatever. So what do we got to do over here? Yeah.
A horizontal line.
Horizontal line, all lines are straight. This is a straight line. Horizontal line at -1 or -2. So the blue graph would be down here. So what your derivative graph looks like is going to be dependent on the original graph. Well, that makes sense because it's the derivative of that function. It's the slopes of that function. All right. 37. The object's moving toward the origin at a steadily, now there's a key word, increasing speed. Moving toward the origin at a steadily increasing speed. So it's going faster and faster. Back towards the origin. So where's it going to start here? Way up here. It's got to be curved. Right? It's got to be curved. Because it's speeding up. So it's going faster, so it's got to get steeper. Okay? Now, there really are no other options here. Right? That's it. Steadily increasing. And the word steadily is key. Because that means what's going to happen over here.
It's going to be a curve. It's going to be straight.
It's going to be straight. It's not going to be curved. Now again, see, I think right now you're making it harder by trying to think of the speed. I think if you think of slopes, it'll be easier on you. What is the slope of this graph right up here? Now the way I drew it, 0. Would it have had to be? It didn't say, but the way I drew it, it looks pretty flat up there. So if the slope is 0 here, that means we have to start this graph at 0. Then what are the slopes as we go along? Gradually what? Yeah, give me numbers. Give me numbers. Like -1, -2, -3. See how it's easier if you have numbers? So the slopes are decreasing. You're right. -1, -2, -3. Those are decreasing numbers, but they're getting steeper. So what that means is our y values need to be 0, -1, -2, -3, right? So that's going to be the line. That's going to be the derivative. And it's going to be a line because of the word steadily. What do I got for my derivative of this one?
Straight. Right, horizontal line, like -1 or whatever.
Down there. Because the slopes of this, that's like -2, -2, -2, -2, -2, -2 slope. So my y values here have to be -2, -2, -2, -2. Okay? We're getting there. I mean, that's going to take us a while. This will be, a week from now, and the rest of the year, this will be automatic. But we're just now getting the sense of it. F prime is the slope. The y values of F prime are the slopes of the F graph. All right, now, 41. This problem usually happens, we usually do this problem right around daylight savings time. It's kind of an interesting coincidence that we have this. Okay? So, I don't know, oh yeah, I know. Okay, so, H is the hours of daylight. Now I know it says hours, time in hours between sunrise and sunset, but it's a lot easier to write it if you just call it daylight hours. That's the same thing, right? Daylight hours, that's what we're talking about. So the H function is daylight hours, okay? Daylight hours. So starting on January 1st is 0, 365 is here, okay? So in January, if we were going to draw an H graph, you didn't have to for this problem, but in January, how long are the days? Pretty short, right? Matter of fact, it's almost, what's the shortest day of the year? December 21st, right in there, right? The winter solstice. Right? That's the shortest day of the year. So right around December 21st. So it's almost, so let's say it's 10 hours of daylight. So in January, are the days getting shorter? January 1st are actually getting longer, right? Because December 21st was the shortest. So it's actually going up, right? It's going up, and now somewhere around the middle, which is what? The summer solstice, which is June 21st, which is pretty much in the middle. I don't care what day it is, pretty much in the middle of the year. That's when it's going to hit its peak, right? Yep. So it's going to be going up, but it's going up pretty slow, so it's actually curving like so. And then it has an inflection point in here when it hits its peak. I missed it. Okay? There actually is an inflection point in here, hits its peak, then it comes back down here, and then it hits its, that's a lousy one. It should hit it, okay, at December 21st, and then it should start back up, and that should correspond to that point, and I don't know if it does or not. But actually, here would be, right, here would be December 21st. Here would be June 21st, right? What would be these inflection points? That would be March 21st, and this would be September 21st. It's a sine function. If you were going to graph the hours of daylight, it would be a sine function. The inflection points would be the equinox, and the local max and mins would be that. Now, none of that you needed to do to answer this question. Okay? So let's do that first, then we'll talk about this. So this would say on the 100th day, whatever that is, April something, I don't know, January, February, March, 30, 90, April something, whatever. On the 100th day,
That was hours. 100
not 100, the input of the function was time in days after January 1st. The output is in hours. The output is daylight hour. So on the 100th day, what'd you say? On the 100th day, or what would you say now after we've talked about it a little bit? 0.05 hours. I hate saying 0.05 hours. Somebody take that times 60 for me so we can get that into minutes. 0.05 hours doesn't make any sense. Nobody would talk like that, right? How long did you work this weekend? Well, 0.05 hours. What? 3 minutes? 3 minutes. Okay, 3 minutes. So it'd be better if that was a 3 minutes. Let's do that. So on the 100th day, what?
3 minutes longer.
It's a rate. So the daylight hour, really good answer would be this. On the 100th day, the daylight hours are changing at the rate of 3 minutes per day, right? The output units are daylight hours. The input is days. Daylight hours per day. Now, somebody said on the 100th day it's 3 minutes longer than the day before. That would be an okay answer too, right? Because you've got whole days, all right? It's not really instantaneous. It's not really a continuous function because you have this day, then this day, then this day, right? So a lot of times they'll say that. They'll say on the 100th day, you've got 0.05 more hours of daylight than you had the day before. Now, why is it more, not less? Because that's a positive number. Right now, H prime would be a negative number, right? Because the daylight hours is decreasing, right? Okay. So just, and then it says when would H prime be negative? Well, we just said that, starting when? Right? June 21st, whatever day that is. The slopes become negative, right? The slopes, H prime's the slopes. Positive until there, whatever. Now, does anybody know that, what's the word equinox? What does that mean? Equal hours, right? On those days, yeah, if you watch the news and they give you the sunrise and the sunset, they're the same, right? Sunrise is at 6:15, it's going to set at 6:15 or whatever. Equal hours of daylight and nighttime. Okay, that's what happens on the equinox. Solstice, what does that word mean? It has to do with sun. It's when the sun stands still. That's where the word solstice comes from, when the sun stands still. Now, what does that mean? Remember, we haven't done it yet, but the problem with the baseball going up to the top and seeing if it hits the roof, right? And we said this yesterday. What has to happen when the ball goes up? What has to happen before it starts coming back down? It has to stop. Its velocity has to be 0. That's what happens with the sun in the sky as well. And that's where the name solstice comes from. In other words, if you thought of, like, for example, this is east, right?
Yeah.
So if we were looking east, south would be to our right. Okay, that's what I've drawn up here on the board. So east, so we're looking east, south would be over here to your right. Where's the sun in the sky? Straight above, a little more to the south, right? Because we're in the northern hemisphere, right? So the sun is a little more to the south as we look up in the sky. So each day, right? So on the longest day, where's the sun? It'd be at its highest point in the sky, right? Still a little bit to the south, but it would be, say, here, right? Now, as the days get shorter, each day when you look up at the sun, what's happening? It's getting a little farther south. It's a little lower in the sky. So June 21st, it's up here. And so now it's moving and it's a little farther south in the sky, a little farther south in the sky, a little farther south in the sky. Now, what's happening? June, you get to June, and the days are nice and long, right? You're out late, it's 9 o'clock, it's still sunny out, right? Having a great time. And on July 20th, do you notice much difference? The nights are still pretty, it's 9, you might have lost a few minutes. It's not changing very rapidly. Look at these slopes. Not very steep, right? But what starts happening in August? You know, you come back to school and everything gets drab and glittery, right? I mean, all of a sudden you come back to school, not only am I back in school, but now the days are getting shorter. And what's happening on the 21st at the inflection point? What's happening to the rate that it's changing at the inflection point? The number of hours you're losing each day is pretty slow here in the summer, but you get here and what's happening? It's going faster. I mean, every day seems like it gets darker earlier and earlier, doesn't it? Until when? September 21st. That's when the daylight hours are changing the most, the fastest at the inflection point, because that's when it's the steepest, because then it starts leveling off again, right? See, now we're getting into October, and especially after the time change here on Sunday, all of a sudden it's going to be, man, it's dark at 6 o'clock, and then it's going to seem like it does that pretty much all winter long. Well, that's because we're down here where it's pretty flat. Okay, that's kind of your inflection point, your equinox. So it keeps going until December. Now, what happens on December 21st? We get to our shortest day. That's when it's the most. So picture the sun, like on a time-lapse photography or something, the sun doing this, right? Farther south, farther south, farther south, farther south, until December 21st, what happens? It starts coming back the other way. Before it can start coming back the other way, it's got to what? Stop. That's when the sun stands still. Solstice. That's why that's called the solstice. Okay? So, interesting connection, I think, to that language and to what we're talking about with slopes and rates of change and stuff like that. All right. You can see I told you we got a lot of stuff here. 42, I'm going to skip that one for right now. 47, I want to talk about that one. All right, 47 says, find the equation of the tangent line. Okay, here it is. When I told you earlier in the year, you've got to know the equation of a line. This right here. This is the type of problem I'm talking about. All year long, we're going to have problems where they say find the equation of the tangent line. You're going to hear it over and over and over again. And it should be the easiest question we deal with all year long. Okay, it should be. It never is, but it should be. Okay, I'm going to keep trying. I've been doing this a long time, and I'm trying to make this easy. But when it says find the equation of the tangent line, you should write that down right away. And what do you need?
Slope
Slope
and a point.
and a point. So, they tell you they want the tangent line at the point 1, 5. So that's good. They gave you that part of it, right? They gave you a point. They said f of 1 is 5. Now, you have to read the directions carefully. The graph they gave you is f prime. Okay? So now, we need the slope. At what point? At the point 1, 5. Now, I don't care about the 5. It's at 1. We have a new way of writing that. That. Right there. That's what we need. Right? Okay? We've always used m for slope before, but now we've got a new way of writing slope, and it's called f prime. So what I want you to do from here on out, whenever you hear the words find the equation of the tangent line, you got to figure out what point they want it at, and you need two things. You need the point and the slope. So that means you need f of 1, and you need f prime of 1. That's the point and the slope. So what's f prime of 1? Well, f prime of 1 is just the output on the f prime graph. Or function. If it's an equation, you plug into it. But if it's a graph, you just get the output. What is that? Remember what we said? The f prime graph y values are the slopes of the f graph, right? So the slope of the f graph is the y value on the f prime graph. So that y value right there is 2. So there's our slope. So we got y equals 2, x minus 1, plus 5. Couldn't be easier, right? Couldn't be easier. If you know what it's saying, what it's asking for, and what you need, right, that's all there is to it. That's the equation of the tangent line. Now, we don't know what the f graph looks like, right? We have no idea, but it doesn't matter. We don't need it. All we need is a point on the f graph and the slope of the f graph, which we get from the f prime picture. Okay? All right. Finally, on 54, I'm not going to go through all of this with you. It's like what we talked about yesterday, but again, if you have some concerns about it, come see me. But I'm just going to quickly go through those 5 things, what you would do, and use your calculator for it. So from what height was it thrown?
74.
74. Okay? That's easy. What was the initial velocity? 38. Was it thrown up or down? Because 38 is positive. Was the height... Now, here's where it gets a little interesting. Here's where you got to really think now. Was the height increasing or decreasing at 2?
Decreasing.
Okay, tell me the various ways you could tell that.
Plug it in your graph.
Plug it into what graph?
Equation.
Which one? We got 2 of them. The top one. Okay, one way would be to look at the height graph. Now, I'm guessing it's a parabola like this. You type in a 2, and it's over here on the downhill part. So that's one way to tell. What'd be another way to tell?
Plug it into the second equation, and if it's negative, then
velocity.
That's the one I really want you to understand. I mean, I agree. You look at the height graph, and at 2, it's on its way down. Okay, I got you. But what if this was a no calculator problem, and I gave you these 2 equations, and said, is the ball's height increasing or decreasing at 2? Without a calculator, without knowing this graph or whatever, right? If you plug a 2 into this, that just tells you how high the ball is. Doesn't tell you if it's going up or down, right? But you plug a 2 into here and you get a negative number. That means the velocity is negative. That means the ball's going down. That's the part I want you to really understand. Okay? All right. D, at what time did it reach its maximum? So we were talking about this. When it gets up to its maximum, what has to happen?
Stop.
So the velocity has to be 0. That's the secret. So it's a question about height, but you don't even use the height equation, at least in the beginning. You say, okay, at the max, now, yes, you could have traced.
Well, you can set the second one equal to 0.
That's what I'm saying. That's what that is. Set the second one equals 0. Now, you could have graphed the H graph. You could have traced. Your calculator does that nice little thing, and it says maximum, right? And so you could have just traced on the H graph. However, on the quiz, if I ask you a question about this, I'm going to word it in such a way that I'm going to want you to do this. right? I want you to understand that the height happens when the velocity is 0. Okay, the maximum height. So you set this equation equals 0. That tells you the time that it was there. What do you do with that then? You plug that back into the height equation. And then that tells you the maximum height. Now, you got to answer the question. If they want to know when it hit its maximum height, then the t that you get is your answer. If they want to know what the maximum height is, you have to plug it back into the height equation. Okay? All right. And that's what they did say. They said at what time and then how high was it. So they wanted to know. How long was it in the air? And that's because you set, well, you probably traced, right? But aren't you going to find when the H graph is 0?
Yeah.
Right? You got to find the time when it's back on the graph, which is when its height is 0. So you could do a solve. Now again, because you have the graph, because these nice calculators will trace for you and all that stuff, but basically you're finding the root or the 0 of this, right? So you could set this equal to 0, and that would be the time it's back on the graph. So that would be how long. Okay, so you can do that on your calculator and go from there. All right. Section 1.5. I really have very little to talk about here. Get your calculators out and handy here.
Logged in.
Yeah, oh, you should be logged in. Yeah. See, now people are going to say, oh, good, if I don't log in, then he won't pick me for presenter, but we're just kind of in that. I want to get this done. All right, so, yeah, go to the calculator screen here. Now, what section 5 is about is what we want to do is we want to just pause for a second here, and we've had this section now where we're talking about this new thing called f prime or h prime or g prime or whatever the function is. Okay, it's the rate of change. All right, it's the slope of the function, and we've started to investigate some things it can tell us, and we're learning to read the notation and all that. And so we want to pause here just a little bit in section 1.5 and say, how could we calculate these slopes? Right? And it goes back to the problem we had the very first day, which was the derivative is the slope of the tangent line. That it's only touching the curve at one point. How can we calculate it? Well, one thing we did, and I'll come back to this in a minute, but one thing we did was this. Okay? So one way we have, so you'll probably have this on a few of your homework assignments, or a few of your problems. One way we have of getting the slope is just this tangent line thing. If all we have is a graph, no equation, nothing else, how are we going to get the slope at -2? Well, we'll just have to estimate. Matter of fact, all of our slopes right now are estimations, unless they give us an f prime graph like this problem, where we could just read the f prime right there, it's 2. But otherwise, it can be an estimation. So one way to do it is this. Sketch in a tangent line, do a rise over run. Okay, but what if we actually have an equation? Okay? What if we actually have an equation? Or what if we have a table of values? Right? Then we could actually do a slope calculation. So this section is going to be all about f of b minus f of a over b minus a. It's going to be all about picking 2 points and calculating the slope. But remember, that's just going to be an estimate of the slope because we really don't know 2 points, right? We only know the 1 point that it's on the curve. If we pick another point on the curve, that is not going to be on the tangent line, right? Remember now, the derivative is the slope of the tangent line. So if we pick 2 points on the curve, you might say, well, let's pick 2 points on the line. Yeah, but we don't know what the equation line is, right? To get the equation line, you need the point and the slope. But we don't know the slope. You see the dilemma, right? So to get the slope of the tangent line, what we're going to do is we're going to pick 2 really close points, like we talked about the first day. We're going to pick 2 really close points on the curve, do the slope, and we'll say that's close enough for right now. Okay? So that's what you're going to be doing. So let's do a table one first, and then we'll have Joe do some on the calculator for us. So let's say you have this table of values like this, and some of your homework problems are going to have this. They're going to have a table of values. And it's going to say find f prime of 2, or estimate f prime of 2. So what are you going to do? Pick 2 points. Which one do you want to pick?
2.1 and 1.9.
I would say it'd be smart to pick those two. I would say if you pick 2 and 2.1, that'd be okay. I would say if you pick 2 and 1.9, that'd be okay. But I would say if you picked 1.8 and 2.2, that would not be smart, right? I mean, let's pick the 2 closest we can, right? Now, if you would argue that it'd be better to pick 1 before and 1 after, I think that's a valid argument, okay? Now, this has a name, this slope formula. We're going to call it the difference quotient. The difference quotient. If you pick 1 on both sides, it's called the symmetric difference quotient. But don't worry about that right now. So show your work here. I really want you to write your work out, just like we were talking about on the quiz. When you write down what it is you're calculating, even though you're using your calculator to do it, write it down. Get in the habit. Get in the habit of showing what it is you're doing. So now this is going to be 6.41 minus 5.61. I really like using the function notation as well. Okay? And so notice you might say, well, that was a waste of time to write both of those. Why didn't you just write 6.41 and 5.61 right away? And I could have. But I really like this idea of getting comfortable with the function notation, because the more comfortable you are with it, every time you see it, it just makes more sense. And there you go. So this assignment is pretty short, and it's all the problems are very similar. They're all about picking 2 really close points and doing a slope calculation. So you're going to be doing a lot of slope calculations. Okay? Now, we call this whole process zooming in. We just zoomed in on the point 2 there, right? By picking 2 really close points. Now, you're literally going to do some zooming in, you know, on the graphs maybe. Well, we did that yesterday in Appendix A. Remember that? We zoomed in till the line was straight. That's literally, physically zooming in. So like right here, I wrote graphically and numerically. To graphically zoom in would be to draw, have your graph on there and zoom in until it looks straight, pick a couple of close points. But there's no sense to really have to physically zoom in to pick 2 really close points, right? If you want the slope of 2, just pick 2 points really close to 2, plug them into the function. So that's what we call numerically zooming in. So when the problem says, estimate the slope by numerically zooming, they're just saying pick 2 really close points. Okay? All right. So now let's say I gave you I think one of your problems has a sine function. So Joe, do this. Go to your, put in sine of x. And let's say we wanted, so for us, let's say we had f is our sine function. And we wanted to know f prime of pi 6. Right? We want to know f prime of pi 6. Okay? So the first thing I would do is, so I want to pick 2 really close points to pi 6. Okay? Well, I better get pi 6 as a decimal in, right? So do that for us, Joe. Go to your calculator screen and do pi divided by 6. Oh, it just gives that. Hit Control Enter. There you go. Okay? So we really are looking for that. So let's do our slope. He's going to do that in a minute here. So let's do our slope. Let's do sine of, let's pick that point, 0.5223 minus sine of 0.524. How about that? Would those be really close to that? 0.523 and 0.524. Those would be kind of on both sides of pi 6 there. And then down here we'd have 0.523 minus 0.524. So if I wanted to know the slope of the sine graph at pi 6 is roughly 0.5235. So I'm going to pick points on each side really close, do a slope calculation, and Joe, what do you get? Oh, I thought you were doing it. 0.523. Now, while he's doing that, think of the sine graph. The sine graph's doing what at pi 6? Going up, right? 0.86607, right? One of you, so jot that down because one of your homework assignments you have to do this. You have to do the slope of the sine graph at several different points, and then they're going to have you plot them, right? Because what that'll give you is the derivative of the sine graph, right? Because the y values, right? The derivative is the y values, the y values on the derivative graph are the slopes of the original graph. But anyway, you got that right there. Okay, so that's mostly what your homework is. We're not going to really do anything new here. We're just going to say, okay, we might be interested in calculating the slope at some points on a curve. How can we do it? Well, right now, the only thing we got is pick two really close points. Do a slope calculation. So that's mostly what your homework's going to be. All right, if you look at the 1.5 homework sheet, I'm sorry, but I want to add two problems. Okay? I suppose if I add two, I could take one away at least, couldn't I? Can I take one away? Let me see if I can take one away. Take two away?
Yeah.
Oh, you guys are. All right, let's take off 1 and 2. And we're going to add 30 and 38. Take off 1 and 2. What those were was where you sketch in your tangent line and do like a rise over run. So if you feel like you need to practice that, do it. 1 and 2 you don't have to do. 30 and 38 we're adding. 30 and 38. Anybody else that's going to be gone tomorrow? You gone tomorrow? No.
Yeah. Give me your hat.
Okay, keep your hats on. Stay logged in. Stay logged in.
We leave after.
Here's an activity. So what we're gonna do. There's gonna be a video
Right here.
on the assignment sheets 1.6 day 1. Okay. Yeah. So it'll be those. Then in class we're gonna be working on this worksheet. And there's a document that I have to send you to your calculator, so log in. And the activity goes with this, so you'll go through the activity and you'll answer my questions on this worksheet. Where do you put these? Just leave them out because I need them next block anyway.